Hello and welcome to the Math 200 lecture series. We are using the Essentials of Statistics by Mario Triola, the 5th edition, and my name is Ray Lapuz. We are now in Chapter 6, Normal Probability Distributions. For our quick preview for the chapter, we will be covering the normal distribution. First, we will study a continuous random variable, a continuous probability distribution, and then we will focus on our normal distribution function. Now, the function itself is a complicated mathematical formula that we don't really need to know. It's shown here, but we will move past that and we will be computing areas that would relate to probabilities. Our first topic will be the standard normal distribution. Before we study the standard normal distribution, though, let us take a look at a density curve. A density curve is a graph of a continuous probability distribution that satisfies the following properties. First, the total area under the curve must equal 1. The areas would represent probabilities, and so here we would see the relationship between the probability and the area, and the whole area is equal to 1. Second, every point on the curve must have a vertical height that is between 0 and some positive value. In other words, the graph cannot be below the x-axis because that would give you a negative probability, and we wouldn't want a negative probability. A simple example of a continuous distribution is a uniform distribution. A uniform distribution has probability values that are evenly spread over a range. So the graph would look like a rectangular graph. And because the total area under the density curve is equal to 1, we would see the relationship between the area and probability. Here's an example of a normal distribution. Suppose that the probability that a randomly selected voltage level is greater than 124.5 volts. So let's say the probability is uniform over a period of 123 volts to 125 volts. And so the height of this rectangle would be equal to 0.5. That's because the horizontal distance between 123 and 125 is 2, and we want the area of the rectangle to equal to 1, so the vertical height must be a constant height of 1/2. 2 times 1/2 is equal to 1. So if we want to find the area that a randomly selected voltage is greater than 124.5 volts, we look at the area under the curve from 124.5 volts to anything that's larger than that. So that gives a horizontal distance of 0.5 and a vertical length or distance of 0.5, and so the area is 0.25. So we have about a 25% chance that we will get a voltage level that is greater than 124.5 volts. Okay, let's focus now on our main idea, which is the standard normal distribution. The standard normal distribution has the following properties. Number 1, it is a bell-shaped curve. Number 2, its mean is equal to 0. And number 3, the standard deviation is equal to 1. So what we're going to do in this section is focus on finding probabilities or finding areas that's related to the standard normal distribution. Later on in this chapter, we will focus on other normal distributions that have a different mean and different standard deviation. So this is the shape of the standard normal distribution. The area under the curve is equal to 1. We have the mean is equal to 0, so that is the very high point of this bell-shaped curve, and the standard deviation is equal to 1. Now our focus is to find probabilities if we're given some z values. So one way to find this is to use table A2. This method is highlighted in a textbook. I will not go over this method on this PowerPoint because I strongly encourage the use of technology, and our main technology for this class would be our calculators. So just to show you the different ways to find the areas using table A2, StatDisk, Minitab, and Excel, you can find these instructions at the end of the section in your textbook. Again, our focus will be using the TI-83 or 84 calculators, and our main command here would be called normal CDF. So you would find that by pressing the second and vars buttons in your calculator, and then selecting the number 2 for normal CDF. Now, the textbook says that this takes in 2 arguments, and it does take in 2 arguments when you're in this particular section. That is, when you're dealing with a standard normal distribution. But in later sections, I want us to get used to doing this normal CDF command for any normal distribution. And so for that, we will add on 2 more arguments in your function. So we're going to have the left z-score, the right z-score, and then the other 2 arguments that I want you to add on is the mean and the standard deviation of your distribution. Now, if it's a standard normal distribution, the mean is 0 and the standard deviation is 1. But later on, we'll be dealing with non-standard normal distributions, and so it would be good practice for us to start inputting the mean and standard deviation for this command. Notation will also be important for us, and here are the possibilities when dealing with normal distributions. You can be looking for a probability that a z-score is between 2 values, A and B. You can be looking at probabilities where the z-value is greater than a particular value A, or you can look at a probability where the z-values are less than a particular value A. Let's do an example, and for this example we will use our calculators. They want us to find the probability that z is less than 1.27. So let's think about this issue, and if you look at the shaded region in your graph, you're looking at everything that goes on to negative infinity all the way up to 1.27. So it would look like the low values would be negative infinity and the high value would be 1.27, and then your mean is 0 and standard deviation is 1 because this is a standard normal distribution. So we're going to take out our calculators, and the only thing left to figure out is how are we going to represent negative infinity. Let's get our calculators here. Negative infinity will be represented by a very large negative number, and I'll show you how to express that. So first we press the second button, vars, and then we're going to select the second one. So you can arrow down 1 and press enter, or you can just simply hit 2, and then now you have the normal CDF. Negative infinity. So negative infinity in our calculators will be represented by a negative sign, and then 1. The E button is a button that sets up a scientific notation. It's right above the comma, but I have to press second first, and then the comma. So that gives my E. This is saying this is 1 times 10 to the, and whatever power I have here, and I'll press 99 to say that's a very, very large negative number. So in reality, this number is negative 1 with 99 zeros. Okay, so that is negative infinity. Now, comma, and then our high number, or the right boundary for the z-score, is 1.27. And then you can end it here, but like I said, it's always good practice to include the mean, which is 0, comma, and the standard deviation, which is 1. So let's close the parentheses and hit enter, and we will see that our answer is going to be 0.897957, etc. Now with this, it's always good to have this rounded off to 4 decimal places, and when you round this off to 4 decimal places, you get exactly what they got here, which is 0.8980. So to summarize, we have our probability that z is less than 1.27 is equal to, and this is our calculator command that we use, normal CDF, parentheses, negative 1e to 99, comma 1.27, comma 0, comma 1, and that's equal to, rounded off to 4 decimal places, 0.8980. Let's try another example. Here we have a similar problem, except we want to find the shaded region that's greater than 1. So in words, maybe we can be asked, using the same bone density test, find the probability that a randomly selected person has a result above negative 1. So above negative 1. So we want to shade in the values that's greater than this. Alright, so the low value is negative 1, and looks like the high value goes off to positive infinity. And so those are going to be our limits, and our mean is 0, and its standard deviation is 1. So back to our calculators, and let's select the second and vars again, and number 2. Okay, now we have a negative 1 for our lower limit, comma, our upper limit is infinity, so I'll press 1, second function, comma, so that's 1e and then 99. Now let's hit 0 for the mean, comma, 1 for the standard deviation, close parentheses. And then we should get the same result that they did, which is 0.8413. That's the same result here, and then we would write down that we're looking for p where z is bigger than negative. Sorry, this should be a negative. Negative 1 is equal to the normal CDF of negative 1, comma, positive E99, comma, 0, comma, 1, and then we get the same result. Let's do one more example where we're looking for the bone density reading between negative 1 and negative 2.5. So that region is going to be given by this last graph over here. And what we want to do now is to use our calculators again. We're going to identify the low value, which is negative 0.25, the high value, which is negative 1, and then use the same mean and the same standard deviation. So we'll press second and vars, number 2, and then we will type in our low value, which is a negative 2.5, comma, the high value, which is negative 1, comma, the mean, which is 0, and then comma, the standard deviation, which is 1. We'll hit enter, and our answer is 1.52445. Now, looking at the answer that they got from the textbook, from the table, they got 0.1525. Actually, the calculator gives a more accurate answer because here they estimated each of these values, and when they had to do a subtraction problem, then their estimate gets less and less precise. So the calculator gives a more precise answer. And so what we have for our result here is that the probability that our z-value is between negative 2.5 and negative 1 is going to be equal to a normal CDF of negative 2.5 to negative 1 with a mean of 0 and standard deviation of 1, and then that result is 0.1524. Again, I really prefer that we use the calculator to compute these because it is more precise, it has less room for error, and we're not so dependent on a table that may or may not be difficult to use, but that's one less sheet that we would worry about. Okay, we have been finding probabilities given some z-scores. Now we're going to go backwards and find z-scores if we know some sort of probability. So here are the directions to find z-scores from known probabilities. They ask us to draw a bell-shaped curve and shade in the region under the curve that corresponds to the probability that we're looking for. So we have to identify whether it's coming from the left or from the right. Now their instructions use the table A2, but we will change this and actually be using our calculator. And we have a new command for this that is called the inverse norm. Let's take a look at an example. So here we're looking at an example where the shaded region is on the left, and that is a 0.95 region. And then we have another region on the right, which is 5%, or 0.05. And what we want to do is we want to figure out the z-value that separates the top 5%. So we want to look at this as our z-value being positive, and we will jump directly to our calculator to find this. So let's go ahead and do that. And the command that we're going to use is called inverse norm. So let's clear the history here and clear this again. We were finished with those other problems. And now let's go to second function and vars. Now we've been using the normal CDF over here. We'll jump to the third one, which is the inverse norm. Now the inverse norm function takes the area to the left side of the z-score that you're looking for. So the z-score that we're looking for is the z-score that separates the top 5%. Now the left side is the bottom half of that, which is a 0.95 area. So let's put 0.95 as our argument for the inverse norm. Just like the normal CDF, it would be good to remember to put your mean, which is 0, comma, and your standard deviation, which is 1. So if we close the parentheses and hit enter, we will get a value of 1.6448. Now generally we want this rounded off to 2, maybe 3 decimal places, and so we would round off to 1.645. This actually is a special value, a critical point value that will be used a lot. We'll come back to that in the next few sections. Here's another example. Using the same bone density test, find the bone density scores that separates the bottom 2.5% and find the score that separates the top 2.5%. So 2.5% here that we're looking for. We see the answers here already because again these are common z-values. We'll see in the next couple of slides that this is actually called a critical value. But let's actually see how they get this using the calculator. First, let's find this negative 1.96. So the idea is that we will be looking for the area on the left side of the critical value we're looking for. So let's say we didn't know what this was yet, but we know that the area on the left side of that number is 0.025. So let's take out our calculators and find the inverse norm of 0.025. Second function vars, number 3, 0.025, comma the mean, comma the standard deviation, close parentheses, and hit enter. So we see that the value is negative 1.9599, so that rounds off to essentially negative 1.96. The next part is a little trickier because we still want to find the value on the left side of this number. So this is the number that we're looking for. What we want to do is we want to find the area to the left side of that. So the area to the left, if the area to the right is 0.025, the area to the left is 1, or I'm sorry, it's 1 minus 0.025, which is 0.975. So knowing that, we can go back to using our calculators and find our inverse norm. So second function, vars, number 3, and this time the area to the left is 0.975, comma, we have our mean, which is 0, comma, our standard deviation, which is 1, and then we're going to get the same number except it's a positive. Now, we know that this is symmetric, we know that this is about 0, so we could have figured this out, that that critical value on the right side would be a positive 1.96. In any case, we found it using the area, the inverse norm function, the area to the left. Okay, let's look at a definition. For a standard normal distribution, a critical value is a z-score that separates unlikely values from those that are likely to occur. So we will be using these ideas of likely and unlikely values in inferential statistics. The notation we'll use is z sub alpha, where z is the z-score, and then alpha is the area to its right. So in the example that we were doing, the value of z sub alpha, where alpha is 0.025, is going to be 1.96. That's the critical value that we found on the right side. Okay, that's the end of section 6-2.